let's get going. Let's talk a little bit more about continuity. Let's start with this example. Find constants a and b so that the following function f of x equal to 2x cubed plus 1 when x is less than 1, ax squared plus b when x is bigger than or equal to 1 and less than or equal to 3, and 4x minus 1 when x is larger than 3. We want to find a and b so that this function is continuous. Just a couple things to be aware of here. Each of these pieces on their own is continuous. 2x cubed plus 1 is a cubic function, or more generally a polynomial. It's continuous everywhere it's defined. Ax squared plus b is a polynomial, whatever a and b are, continuous where it's defined. And 4x minus 1 is also a polynomial, continuous where it's defined. So the only places where we're concerned where this might be discontinuous is where you switch from one piece to the next. Where we switch from the 2x cubed plus 1 to the x squared plus b, which is at x equals 1, and where we switch from the x squared plus b to the 4x minus 1, which is at x equal to 3. So we need to talk about continuity at x equal to 1. So continuity at x equal to 1. And when I'm thinking about continuity, I'm always looking to show the three things we need to show are true for continuity. So thing one, we need to show or find what the function is defined to be at 1. So if I plug in 1, I'm going to get, well, if I plug it into the place where it's defined, I'm going to get a times 1 squared plus b, which is a plus b. Okay, not very exciting. The second part is really what matters here. We need to show that the limit as x approaches 1 of f of x exists. To that end, and for most piecewise functions to that end, you need the left and the right hand limit to be the same. So we need the limit as x approaches 1 from the left of f of x, which is going to utilize this piece of the piecewise function, the 2x cubed plus 1, because that's where x is less than 1. We need that to equal the limit as x approaches 1 from the right, which is the limit as x approaches 1 from the right of ax squared plus b. Fortunately, finding these limits is really straightforward. We're just going to plug in 1 to each of them. So on the left-hand side, we get 2 times 1 plus 1. On the right-hand side, we get a times 1 plus b. Which is not super duper helpful. I mean, it's helpful, but it doesn't allow us to specifically find what a and b are yet. But it's going to help us. And then we need these to be equal for the limit for the function to be continuous. But that's kind of maybe not obvious, but no, it's pretty, I think it's pretty obvious, right? If the function is equal to a plus b, and we need a plus b to equal 3 for the limit to exist, then it's going to be 3, but we need to figure out a and b are. So now let's look at the other point. Let's look at, or I should say the other x value, continuity at x equal to positive 3. So now the same sort of thing. We could probably bypass saying what f of 3 is. I mean, you can plug it in. F of 3 is going to be a times 3 squared plus b, which is 9a plus b. But then the real important part is the limit part. If I look at the limit as x approaches 3 from the left, I'm going to be using the middle piece of the function where x is less than 3. And I'm going to need that to be equal to the limit as x approaches 3 from the right, which is going to use this last piece of the function, which is 4x minus 1. Again, taking these limits isn't terrible. We're just plugging in x. And again, whenever you're finding a limit, that's usually the first thing you want to try. Can I just plug in what x is approaching? So plugging in x equal to 3, I'm going to get 9a plus b equal to 4 times 3 minus 1, which is 11. And now we have 2 equations and 2 unknowns. We can certainly solve for a and b. I would probably, I don't know, there's a number of ways you could do this. I would probably solve for one and plug it into the other. So I'd probably do my work over here and say, all right, using this equation here, b is equal to 3 minus a, substitute that in here and get 9a plus 3 minus a equal to 11. So then I have 9a minus a, which is 8a plus 3 equal to 11. So 8a equals 8. So a equals 1. And then plugging that back in here, we're going to get b equal to 2. So those are the values of a and b that make this function continuous.
Basically, just equate the limit at the two endpoints such that the left and the right side are.
Yeah, because the limit has to exist at every point in this function, specifically at x equals 1, x equals 3. Other questions about this? One more example. Yeah, let's see here. So let's say the following. Break this one a little bit differently. So where is f of x equal to the following? Let's see here. Square root of 2x plus. Sorry, I'm trying to make up something that's relatively not terrible. Sure, 2x plus 14 when x is less than 1. And then the sine of x. I blew it. I knew I was going to make that mistake. Oh well. The stars were. Apologies. Sorry. I thought I was making something cool and I blew it. I'm gonna fix it. It's gonna be all right. I could almost fix it, but no. I'll write it. It's gonna be almost the same. Apologies. Where is this function continuous? Two x equals 16 when x is less than 0, less than or equal to 0. Sine of 4x over x when x is bigger than 0 and less than, let's make it interesting here, pi over 6. And finally, cosine of 2x when x is greater than or equal to pi over 6. So where is this function continuous? So let me ask all of you, where is one point for sure where we might be concerned about continuity? 0. Where's another point? Right. And now I will point out there's actually a whole slew of points where it's not continuous because it's not defined there. So just as a kind of quick aside here, notably, this function is undefined if 2x plus 16 is less than 0, which means 2x is less than negative 16, x is less than negative 8. So technically, this function is actually undefined quite a few places. So not that we're really going to worry too much about that, but when we talk about where it's continuous, it's not going to be continuous for x being negative. So our interval of continuity, like our answer, is going to be starting at negative 8 and then going up to maybe stopping at 0, maybe not, maybe stopping at pi over 6, maybe not. All right, this function is completely undefined when x is less than negative 8. Okay, well, let's look at 0. So is it continuous at 0? Well, we have to answer 3 questions. Does the function exist? So let's look at x equals 0 here. So f of 0, we plug it in, we get the square root of 2 times 0 plus 16, which is the square root of 16, which is 4. Great. So now we know that not only do we need the limit to exist, but what does the limit need to equal? 4, otherwise it won't be continuous. So if either the left or the right hand limit doesn't equal 4, we're done. Because we know that if the limit exists, it will not be 4. If the limit doesn't exist, it won't be continuous. So either way, if one of the one-sided limits doesn't exist, you can kind of stop. So let's look at the limit. We know the limit as x approaches 0 from the left-hand side. We're just going to use the same piece, and we're going to get the same result. You're going to get 4. From the right-hand side, the limit as x approaches 0 from the right of sine of 4x over 4, sorry, over x, apologies, is a 0 over 0 type of limit. Plug in 0, you get sine of 0 over 0, which is 0 over 0. And this is one of those ones where we have to use the idea about the fact that sine of a thing over the same thing that's going to 0 has a limit that's 1. So we're going to rewrite this as a limit as x approaches 0 from the right of sine of 4x over something times something over x. And the thing we want to be beneath sine of 4x is 4x. So then we write another 4x on top to accommodate for that. The limit of this, that goes to 1. This simplifies to 4. So we do in fact get 1 times 4, which is 4. So the limit from both sides is 4, which means, great, we have that the limit as x approaches 0 of f of x is equal to 4, which is equal to f of 0. So the function is continuous at 0. Let's look at the other point. So when I ask these kind of questions, it's almost always pretty likely that one of the points is going to be continuous and one of the points is not going to be continuous. I'm not saying your teacher is going to do that. I'm just saying it's often what happens. So let's look at the other point of interest, which is pi over 6. Okay. So keep this on the page here. Oh, it kind of works. All right, sure. So now let's look at x equal to pi over 6. And I'm going to plug in pi over 6. So f of pi over 6 is going to be cosine of 2 times pi over 6, which is cosine of pi over 3, which is 1/2. So now we need to look at the limit. So step 1, the function certainly exists there. Step 2, the limit as x approaches pi over 6 from the right is just going to be the same. Pi over 6 from the right is still that same piece of the function. So we can just say that's equal to 1/2. We don't have to do any more work than that. But then we have to do the limit from the other side of pi over 6. So limit as x approaches pi over 6 from the left. And then we're going to be using the sine of 4x over x. You just want to say over 4. Sine of 4x over x. Well, we can just plug it in, right? That's certainly allowed. It's not a 0 over 0. It's just a sine of 4 times pi over 6 over pi over 6. And if we evaluate that, we're going to get sine of 2 pi over 6, which is pi over 3 over pi over 6. And sine of pi over 3, well, if you know that cosine of pi over 3 is 1/2, we know that sine of pi over 3 is root 3 over 2. That's going to be the square root of 3 over 2. And instead of dividing by pi over 6, let's multiply by the reciprocal, 6 over pi. So this ends up being 3 root 3 over pi. Whatever that number is, I'm pretty darn sure it's not equal to 1/2. I don't know exactly what 3 root 3 over pi is, but it's definitely not 1/2. Yeah. Yes, apologies. Yeah. Sorry about that. Yep, that's a 2 pi over 3. Fortunately, sine 2 pi over 3 is also root 3 over 2. So our answer didn't change. But yes, you're right. Definitely is 2 pi over 3. I was just thinking about pi over 3 part, but yeah. So all right, this is root 3 root 3 over pi, which is not equal to 1/2. And so we can say, well, f of x is not continuous at x equal to pi over 6 because the limit as x approaches pi over 6 of f of x does not exist. Okay, so back to answering the question. We've shown it's continuous at 0. We've shown it's not continuous at pi over 6. We also know it's not defined if x is less than -8. So we're going to say it's continuous on the interval from -8 to all the way up to pi over 6, and then everything after pi over 6. Not continuous if x equals 0, or sorry, if x equals pi over 6, sorry, or if x is less than -8. All right, let's see. I got one other thing here. Yeah. Have you guys talked about the intermediate value theorem? I see some nods, some shaking heads. Okay, well, we should talk about it briefly. It does certainly get brought up on occasion. It's an important theorem. It's also graphically not too hard to understand. So here's the intermediate value theorem. So the intermediate value theorem says the following. And I think it's really kind of easiest to draw a picture first. So let's draw this picture. Let's say we have a function. Maybe it looks something like this. I'm just going to graph part of it. So here's the point A, B, here's f of A, here's f of B. So here are the words I'm going to say before I actually write out what the theorem is. The theorem just says that if you have a function that's continuous, and on some interval you get all these y values, then on this interval you should be able to get any y value between those two y values. So I have f of A is some lower y value, f of B is some upper y value, and anywhere between A and B, I should be able to find a point that corresponds to any value between f of A and f of B. So I could pick some y naught right here and say, okay, well, for that y naught between f of A and f of B, there has to be some corresponding C value between A and B so that f of C is equal to that y. That's what it's saying. Basically, it's saying if the function's continuous, you get all the y values between your lowest and your highest y value. I should say your beginning and your end y value. No, I did. That's why I just clarified between your beginning and your ending y value. You're not guaranteed to get that. But the thing is, but we're pretending that so here's what I'll tell you. You don't get to see the whole function. All you get to know is that the function goes that low and goes that high. So all you know is that that's how low and how high the function goes. So with that limited knowledge, all we can say is, well, knowing the function goes that low and that high, I can get any other y value between those two y values and say that there is some x value between A and B that gives you that y value. Exactly. Maybe it doesn't actually go that high. Right? Maybe your function doesn't look like that. Maybe your function looks like something more like this. And the point is that all we know about the function is the beginning and the end value. Exactly. So here's what the intermediate value theorem says. If f of x is continuous on the closed interval AB, then it takes on every value at least once, maybe more than once, at least once, between f of A and f of B. Written maybe a little more mathematically. So this is like the nicer way of saying it. I feel like this is like, okay, this makes sense. We get maybe I should add one little thing here. It takes on every y value between f of A and f of B. Here's the more mathy way of saying it. If f of x is continuous on the closed interval from A to B, then for every y naught between f of A and f of B, there is a number C between A and B such that f of c is equal to y naught. These two definitions say the same thing. One of them is just a little mathier. Question? So that's actually a really good question. So what if it wasn't a closed interval? Let's look at an example. So let's say our function f of x, I'm going to make it real easy. Let's say it's equal to 2x plus 1, and we're on the open interval from, let's say, 3 to 7. Oh, you need something from the people? Sure. The last little part says there's a number c between a and b such that f of c equals y naught. So basically, all we're saying is that just like in this picture here, for every y naught between a and b, so pick any y naught between, sorry, f of a and f of b, you pick some y value, there has to be a corresponding c value between a and b. It has to live between on your interval that you've already been given, like that. Okay, so let's say we got this one. So this is gonna sure. That'll be fine. So the problem with this one is we're gonna be starting at the point 3, 7 and ending at the point 7, what, 15? Yeah. So the issue here is that there isn't the highest y value. There isn't the lowest y value. So on this interval, what's the biggest y value this function takes on? Well, it doesn't though. So just give me a number. What's the biggest number this function gets to? Okay, how close to 15? Right, as close as we want. How close is that? Right, but the thing is we don't actually get to 15, which is what the limit is. So the thing is, if we have an open interval, we don't have a highest y value necessarily. We don't have a lowest y value necessarily, and that's a problem for this theorem, because the theorem says we have some upper f of a or some highest value, some lowest value that we're looking at as our endpoints. There isn't that. So let's look back at what the theorem says. So the theorem says we're going to take on every value between f of a and f of b, but we don't have an f of a and f of b to really talk about it. So that's why we're kind of having an issue here, because there aren't endpoints to even deal with in the first place.
So if you just alter that between the right limit of the and the left limit of the
Sure, that might work.
That's not the theorem.
That's not the theorem. So we really do need all these things to be true, especially we also need to be continuous. For example, if it wasn't continuous, let's say we had a function like this. Make something up here that's really fun. Then we had a function that did this kind of deal. Then okay, so this point's the point 2, 1. Here we've got 3, 3, 3, 4, 5, 2. I know it's kind of wacky. Now, we do get every y value between our lowest value and our highest value, right? Well, actually, so I'll take that back. Well, I keep saying lowest and highest, and I'm misspeaking here. So if we look at this here, our interval, bless you, is from 2 to 5. And we are saying, okay, well, is it true that for any value between f of 2 equal to 1 and f of 5 equal to 2, that there is a corresponding y, or I should say a corresponding x, so that f of x is equal to y. And the answer here is actually yes. So you can fail to meet the criteria of the theorem and still have the result be true. And you can say, well, I didn't meet all the things I needed, but still, yeah, for any value between 1 and 2, I can find the next value that gets me there, right? Because I can think, if I pick like this value here, there is definitely a corresponding C value that outputs that. So when we're talking about the intermediate value theorem, it's really important to say that even though you might be missing some stuff, you don't want to falsely conclude that you're using the theorem when you're really not. So let me back up a little bit. Let's look at another example. Let's say that we have the following. Here's a nice regular function, nothing bizarre about it, x cubed plus x minus 7. And we want to show that this function equal to 0 has a solution on, let's say has a solution. Great. I don't know what the solution to that is. Like really, solving that is moderately hard. Like I couldn't solve that without doing a lot of Googling probably, because I don't know what the answer is. And solving a cubic, although it is not a lot more difficult than solving a quadratic, it's something we don't really learn. Like solving the quadratic formula, right? Everybody knows it. Solving a cubic, there are formulas for it, but it's something we're not typically taught. And there's not an easy answer to this. But the thing is, we're not asked to find the solution. We're asked to show the solution. So let's think about what's going on here. So I'm going to pick some values for x. Let's pick something easy. Let's pick x equal to 0. If x is 0, f of 0 is going to be 0 plus 0 minus 7, negative 7. And let's just go up the ladder. Let's pick x equal to 1. F of 1 is going to be 1 plus 1 minus 7. Okay, that's still negative. Let's pick x equal to 2. F of 2 is 8 plus 2 minus 7. Great, that's positive. I was looking for a value that gave me a negative output and a value that gave me a positive output. Here's why. I know that f of x equal to x cubed plus x minus 7 is continuous. It's continuous everywhere. And that's true for any polynomial. You can always, without any worry, if you see something's a polynomial, you can automatically say, it's continuous, it's differentiable. You don't have to worry about justifying it. No one's going to quiz you on, is that polynomial really continuous? It's a fair assumption to make. You're always going to be with that. So it's certainly continuous on whatever interval I want to pick. I'm going to pick the interval starting at 0 and ending at 2. Okay, great. Also, we just said that f of 0 is negative 7, which is certainly less than 0. And f of 2 is positive 3, which is certainly greater than 0. So since my function is continuous, and it goes from f of a being negative to f of b being positive, it has to hit every y value in between. Specifically, y equal to 0. Graphically, here's how things are looking. F of 0 was negative 7. F of 2 was positive 3. And because my function's continuous, I can't just hop over the x-axis, right? I have to actually cross it. And somewhere right there, there's going to be a value where that function is equal to 0. I don't know what it is. That's okay. I wasn't asked to find what it is. What I can say is, by the intermediate value theorem, there must be a number c, and it has to be between the two x values I've already used. And in this case, I've used 0 and 2, although you could have used 1 and 2. Between A equals 0 and B equals 2, such that f of c equals 0. This is often what we use the intermediate value theorem for, is to show that something that we can't really solve still has a solution. It's kind of the number one thing. Like most of the time when you're talking about the intermediate value theorem, we're using it to show that there's a solution to an equation, even though we can't find a solution. Another very common example of this is to show that, I can move this paper here, is to show that cosine of x equal to x has a solution. Graphically, it certainly seems like it should. If we graph cosine of x, it's been a while. The cosine of x looks moderately like this. And y equals x looks about like that. It certainly looks like there's a point where they are crossing each other, where you're getting a point of intersection. So it seems reasonable to say, well, there is a solution. Right? It certainly looks like there's one. But I don't know what it is. I could use a graphing calculator to approximate if I really wanted to, but that's not what I'm asking us to do. I'm asking us to show there's a solution. So how do I show this solution to cosine x equals x? Well, the first thing is showing one function equals another function is always a pain. Instead, showing something else equals 0 has a solution is the easier way to go. So instead of showing that this has a solution, I instead want to show that cosine of x minus x equals 0 has a solution. Or if you prefer, x minus cosine x equals 0. Either way is totally fine. So then we're going to do the same thing we did before. We're going to say, okay, I'm going to call, it's usually a good idea to say the thing you want equal to 0 to call it a function name. Let's call it g of x. So we're going to try and show that g of x equal to 0 has a solution by doing three things. One, I wouldn't say showing, I would say observing, commenting, making a note that the function is continuous, at least on the interval that we're going to use. Two, finding a place where it's positive and a place where it's negative to show that it has to go through 0. And three, kind of writing it all. So, first things first. Observe, note, say something somehow about the fact that g of x equal to cosine of x minus x is continuous everywhere. And it is. Cosine of x is a trig function, specifically cosine or sine, are both continuous everywhere. And y equals x is also a function that's continuous everywhere. It's a polynomial. And if you add or subtract two functions that are continuous everywhere, you still get functions continuous everywhere. So it's definitely not a leap to say cosine x minus x is continuous everywhere. Thing two, we want to find two values where one is positive and one is negative. I'm almost always going to start with 0 if I can. 0 is an easy thing to plug in typically. So if I plug in 0, g of 0 is going to be cosine of 0 minus 0, which is 1 minus 0. Which is... If I think about my graph here, I just picked here and I said, okay, this minus this was positive. So if I'm really looking at this, I should probably be trying to pick a point over to the right of this point to show that the subtraction is going to give me the opposite value, give me something negative. So I might try picking pi over 2. I could probably go smaller, but there's no reason to in this particular problem. So if I look at pi over 2, g of pi over 2 is equal to cosine of pi over 2 minus pi over 2, which is equal to cosine of pi over 2 is 0. 0 minus pi over 2 is negative pi over 2. Sometimes they make this problem harder by saying it has to be like between 0 and 1. And you have to work a little bit harder. We can talk about it in a second. But let's finish this up first. So then part 3, we've got everything we need. It's continuous. It goes from a positive value to a negative value. If you go from positive to negative and you're continuous, you go through 0. There's no other choice. So by the intermediate value theorem, I always like to say the following words. There must be a number, and I like to say where it lives. There must be a number, we usually call it C, and C has to be between these two values. That's like our A, that's like our B. Between 0 and pi over 2, such that G of C is equal to 0. Question, yeah. All right, go ahead and ask the question. I just picked them, exactly, yeah. Really? Okay, all right. Totally work, all right, fine, whatever. So yeah, so sometimes they will give you the interval and they show there's a solution on this interval, and usually picking the endpoints is the easy way to go, like the usual work. But sometimes they won't give you an interval and you kind of have to just start. And so I picked 0 because it's easy. And picking 0 gave me something positive. So then I knew I was trying to pick a different value of x that would give me something negative. And I knew that pi over 2 was a good choice for 2 reasons. 1, it's easy to find cosine of. And 2, pi over 2 is bigger than 1. It's like 1.5-ish. And cosine is never bigger than 1. So cosine minus something bigger than 1 had to have been negative. So I knew I was picking something that was going to work. If someone tried to make this problem a little bit harder and said, well, now I want you to show the same thing, except show that cosine of x equal to x has a solution on the interval from 0 to 1. It's the same sort of work, but it's a little bit harder because 1's not a great place to plug in. There's 2 ways to go about doing this. One way is still to just use what they've given you. So we're going to say g of x is cosine of x minus x. Great. And then we're going to use the 2 points. So g of 0 is still the same as it was before. Okay, g of 1 is cosine of 1 minus 1. I don't know what cosine of 1. I know that 1 radian is about 57 degrees. I know that cosine of 60 degrees is about 1/2. So I'm pretty sure that's close to 1/2, but I don't actually have an exact number to write down. But that's okay, because here's what I definitely know. I definitely know that cosine of 1 radian is not equal to 1. Cosine of 0 is equal to 1, right? 0 radians over here. And then the next angle where cosine is equal to 1 is how many radians? We go all the way around the circle. 2 pi radians. Is 1 equal to 0? No. Is 1 equal to 2 pi? Thank you. Okay. So 1 is definitely not 0, 1 is definitely not 2 pi. And at 0, cosine is equal to 1, and then the next place you get 1 is 2 pi. So if you're taking cosine of an angle that's not 0, and it's not 2 pi, but it's between 0 and 2 pi, it can't equal 1. It has to be strictly less than 1. So this is strictly less than 1. Here, let me show you what I'm saying, just to make sure everyone's on board here. Unit circle. Right here, theta is 0. The point's 1, 0. There's cosine of 0. And as you go around the unit circle, oh, look, my x value is smaller. So all these points here, whatever the angle is, cosine is less than 1 because the x coordinate is less than 1. As we move over here, cosine's negative, 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 right? Back here, back here at theta equal to 2 pi is the next time that the cosine function gets to equal a value of 1. So I know that at 1 radian, right, when we plug in an angle of 1 radian, which is about there, the cosine value is definitely less than, for sure. But that's the argument I'm using to say, well, I don't actually know what it is, but I know that's less than 1. And if this is less than 1 minus 1, it's certainly less than 0. That's kind of the trickier way to do this problem. The maybe less tricky way of going about it is saying, well, I'm still going to have the same thing. I'm going to have g of x equal to cosine of x minus x. And then instead of doing this crazy thing where I try and find cosine of 1, I'm going to still do g of 0, which is 1 minus 0, which is 1. And then I'm going to pick a value that is less than 1 that's easy to find cosine. So what's an angle that's less than 1? In radians, I can find cosine. Pi over 4. You could also try pi over 6, but I don't think pi over 6 actually works. I think pi over 6, yeah, I don't think it works. Pi over 4 does. If I look at pi over 4 is certainly less than 1. G of pi over 4 is cosine of pi over 4 minus pi over 4, which is the square root of 2 over 2 minus pi over 4. Okay. That's going to be 2 root 2 over 4 minus pi over 4, which is 2 root 2 minus pi all over 4. And now we need to know approximately, okay, root 2 is about 1.4, 2 times root 2 is about 2.8, and 2.8 minus pi is definitely negative, so we're good to go. So that's how people attack this problem typically. They say, well, I can say for sure from this that g of x equal to 0 has a solution for some number between 0 and pi over 4, which is certainly contained in the interval from 0 to 1. Right, we picked a smaller interval, so there was a solution in there, and then that means there has to be a solution in the somewhat larger interval. Basically, on a number line, we said, okay, I want to show there's a solution in there. And instead, I said, well, I'm going to do you one better. I'm going to show you that there's a solution in here instead. Which definitely means there's a solution in the larger interval. Okay. Kind of all of my names. So intermediate value theorem, at the end of the day, really just says a continuous function takes on all y values from its beginning y value to its end y value. Maybe it has some lower ones, maybe it has some higher ones, but definitely you get all the ones in between. Question? Right. Well, so we can't use the intermediate value theorem if the function is not continuous on the interval in question. So for example, someone could give you something like, show that f of x equal to 1 over x minus 2 at, trying to think about how I want to write this here. Yeah, so it has a value between x equal to 3 and x equal to 7, such that f of x is equal to 0.3. We can actually solve it, right? You can definitely go right ahead and solve this equal to. The only thing that we have to worry about here is that, is our function continuous? Well, not everywhere. Where is that function discontinuous? Right. But as far as the interval that we're talking about is concerned, it's totally continuous on that interval. So we can say, well, yeah, certainly f of x is continuous on the interval in question. And 2, we can see that f of 3 is 1 over 3 minus 3, which is 1. And f of 7 is 1 over 7 minus 2, which is 1/5, which is 0.2 if you like decimals. So certainly by the intermediate value theorem, there has to be a place between 3 and 7 where f of x is equal to 0.3. So we can certainly say by the intermediate value theorem, there is at least one, there might be multiple numbers, but there's at least one C between 3 and 7 such that f of C is equal to 0.3. Now, in this particular example, and actually in a fair number of examples, you can often find what that value of C is. Here we totally can. So if we actually just solve f of C equal to 1 over C minus 2 equal to 0.3, we can figure out what C is without too much effort. I would probably choose to write this as a fraction. So I have 1 over C minus 2 equal to 3/10. And cross multiply, 10 equal to 3 times C minus 2. 10 equals 3C minus 6. 16 equals 3C. So C is looking like 16/3. Or 5.333333 forever. So there definitely is a C between 3 and 7. We found it. It was 5 1/3, such that there is a solution to this equation. But yeah, I mean, there's not a lot. I will say there are typically not a lot of great questions that we can really ask that make you use the intermediate value theorem. So that's why they're kind of maybe seem kind of easy, because there's not a whole lot of variety when it comes to that. There is kind of one other thing we do when we have one other thing later on, which we will talk about later on. All right, what time is it? 10:48. Okay, we should definitely keep moving because we should talk about the limit definition of the derivative. So let's move on to the next thing. Limit definition of the derivative. Let's look very, very generally. Yeah. Let's look at an example and we'll kind of generalize it. So we're going to find the derivative of f of x equal to x squared at the point, or really actually just anywhere. Not at. So here's what I want you to think about graphically. We've got our function x squared. And the idea here is that when you're trying to find the derivative of a function, what we're trying to do is we're trying to find one interpretation is the slope of the tangent line at any given point. So we're going to pick some generic point. X comma f of x. And instead of finding the slope of the tangent line, because I don't know how, right? I don't know how to find the slope of a line through one point, I'm going to grab another point. I'm going to grab a point up here. I'm trying to give myself enough room so that I have a little ruler with me. Thank you. Love this ruler. Great. So here's another point over here, which I'm going to call x plus h comma f of x plus h. I've just moved over a little bit by h. So there's x. There's x plus h. In case it isn't clear, the difference between them is h. Okay, so what we're going to do is we're going to find the slope of this secant line. Okay, so I know how to find the slope of a line between 2 points. Not terrible. The slope of this secant line is going to be the difference in the y's, which is f of x plus h, f of x, all over the difference in the x's, x plus h, minus x. And I'm going to simplify that just a tiny bit. I'm going to cancel the x's in the denominator. So I'm going to have f of x plus h minus f of x all over h. In this particular example, we're going to get that the slope of the secant line is going to be, well, our function is x squared. So we're going to have x plus h squared minus x squared all over h. That's the slope of our secant line. And we can simplify this, right? Multiplying out x plus h squared, we're going to get x squared plus 2x h plus h squared minus x squared all over h. We can cancel some stuff. X squared minus x squared is 0. We're left with 2xh plus h squared divided by h. We can factor out an h from the top. We're left with 2x plus h over h. H divided by h is 1. So we're left with just 2x plus h. So the slope of this secant line is 2x plus h. And now here's the big idea. Here's where we're going with this. We're going to let that point get closer to that point. So we're going to say, okay, well, what happens if you move this point over here now? Well, now look, try and draw it again here. Whoops. My secant line now looks like that. And it's getting closer and closer, right? If I pick points that are closer and closer, I don't want to draw anymore because it's going to make my picture look terrible. If I pick points closer and closer, we're eventually going to get to where our secant line is approaching having the same slope as the tangent line. So what we're going to do is to find the slope of the tangent line, we're going to take the limit as this point approaches that point. So you could say as x plus h approaches x, but I'm going to say as h approaches 0. I'm going to the difference between them get very, very small. So the limit is h approaches 0 of the slope of the secant line. That is how we are generally finding the slope of the tangent line at any value of x. Or in other words, how we're finding the derivative. So this is the derivative of this function at any point. So for this particular function, if we take the limit as h approaches 0 of what we just found, we get just 2x plus 0, which is 2x. So for our function, f of x equal to x squared, we just found the derivative to be 2x. Question? So let's talk about, so here's why we're doing that. I'm trying to find the well, I'll get there in a second. Okay. So let's look at a more general example, and then we'll kind of talk about why we're doing what we're doing. So let's say we had, actually, now I feel like, so let me actually answer your question now that I think more. So the reason we're squaring this is because we are plugging that x plus h into the function. So we're saying, I want, like, for example, if this was the point, 3 comma something, I want to plug that 3 into my function and square it. So I'm going to get 3 comma 3 squared. Exactly. Right, because I'm finding f of whatever's in there. F of x would be x squared, f of 3 would be 3 squared, f of this would be this stuff squared. Question? So the 2x plus h is the slope of the secant line. And then to find the slope of the tangent line, we take the limit as h goes to 0 to get the slope of the tangent line, which is just 2x. So the h kind of becomes inconsequential. So let me write down a couple things here. So let's say we had a function that looked like that. And I really want to find the derivative right there, which I'm going to call x. That's the point x, comma, f of x plus h. So a couple things about derivatives in general. One interpretation of a derivative is the slope of the tangent. That's probably the most common way people talk about it. But when we talk about slope, Slope is just the change in y over the change in x, or how y is changing as x is changing. So when people talk about derivatives, the words they would be better to use are more generally are rates of change. You're asking about how one thing is changing as another thing is changing. Fair question. This is x. That actually says, yeah, you're right. It does say the wrong thing. Let me draw a picture again. The point I wanted was actually x comma f of x. So yeah, is the slope of the secant line. You're totally right. Those are all right things. I would say the only difference between the secant line slope and the tangent line slope is that for the tangent line slope, we are taking the secant line slope and then taking the limit of that. So let's draw this picture and kind of see if we and ask all the questions as I go. So we've got these 2 points. And this point here, I'm just going a little bit over to the right. I'm saying, well, I'm going to add on h. Right, so this distance here between x and x plus h is just h. Notably, if h gets smaller, x plus h is going to get closer to x. So as we move in this direction, where this point moves towards that point over there, h is going to approach 0. And currently our thought is, well, I want to find the slope of this tangent line. That's what I'm interested in. I want to find the slope of the tangent line. Before I can do that, we're going to find the slope of the secant line. So we're going to say, well, I know how to find the slope between 2 points. That's something that we've been good at for a while now. But I want to find the slope of this secant line. Well, it's just like what you were saying. It's an average rate of change. It's the difference in the rise, the y's, over the difference in the x's. So this point over here, which is our, I don't know if I'm going to write it, our x plus h, comma f of x plus h. That's our other point. And so, maybe I don't know what's happening over here. Okay. It's interesting. I'm not sure why that's happening. I have to talk to someone about that. So this secant line, slope of a secant line, right? Just the difference in the y. So this y value minus that y value. So f of x plus h minus f of x divided by this y value minus that y value. X plus h minus x. And in the denominator, it's really straightforward. Just can't to have x minus x be 0. So x minus x, those equal 0. And you're left with f of x plus h minus f of x all over h. And that is the slope of the secant line. Now here's again the idea. We're going to let this point get closer to that point. So as that happens, look what happens to my secant lines. I'm going to try and draw them so they don't look like trash, which is, a tall order here. Here's my next secant line. It's getting a little bit closer to being the tangent line. And if I draw a point even closer, there's my next secant line. Even closer to the slope of the tangent line. So as you move those points closer, the secant lines have slopes that are tilting closer and closer to being the slope of the tangent. And that is really, honestly, the whole idea with this limit definition. If you're taking the slopes of these secant lines and just saying, okay, let the points get closer and closer together so that the secant line starts looking like it has the same slope as the tangent line. The whole shebang. So to find the slope of the tangent line, we take the limit as h approaches 0. Or if you prefer to think of it as x plus h gets closer to x. Same thing, right? If x plus h is getting closer and closer to x, that means the difference between them, which is h, getting smaller and smaller and smaller. Of the same expression, f of x plus h minus f of x all over h. Couple things here. If you just plugged in 0 for h, what would you get on the bottom? What would you get on the top? F of x minus f of x, which is 0. This is why we have been practicing 0 over 0 types of limits, because all these limit definition of the derivatives all are 0 over 0 types of limits. So that's why we need those tools to evaluate them. So what I'll say is, for a function f of x, we define the derivative to be f prime of x equal to this limit. The limit is h approaches 0, f of x plus h minus f of x all over h. Questions, comments, observations before we do some examples?
On an example, would we have to show how we can do that equation?
No.
Okay.
There is an expectation for sure that you memorize this definition. So if anyone ever says the definition of the derivative, or more likely the limit definition of the derivative, this is what they mean. You're expected to know it for sure. Okay. So let's look at some examples. Like, find the derivative of f of x equal to x to the third. So we're just going to throw this into the definition. I personally like to rewrite the definition every time I do it, so I know what I'm doing, but you don't have to. So I'm going to say that f prime of x is equal to the limit, as h goes to 0, f of x plus h minus f of x all over h. There's f of x already written down for me. F of x plus h, I do like to write it down on the side. So here's what I would recommend if you're getting a little caught up. F of x is x cubed. F of parentheses is parentheses cubed. It'll always work to say, well, whatever's in there is going to get cubed. And then what's in there in this case? Oh, it's x plus h. All right. So then we're going to write this out as the limit as h goes to 0 of x plus h cubed minus x cubed all over h. X plus h cubed. Okay, here's x plus h cubed. I'm gonna say what it is this time, and then for the next one, I'll show you the trick. So x plus h cubed is x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed all over h. There is a trick for that, but hold on. We'll show it for the next one where it's even more impressive. Okay. So here's what's usually going to happen with these limit definitions of the derivative. Your goal is to evaluate this limit. It's a 0 over 0 type of limit. Almost always, like always. And our end goal before we can take this limit is to get rid of that h in the denominator. If that h in the denominator is causing us problems, making us divide by 0, we want it to go away. For it to be able to go away, we need to be able to factor out an h from the numerator so that we can then have h divided by h giving us a 1, canceling out the h in the bottom. For that to happen, all of the not h terms in the numerator need to cancel out. And that's usually going to happen right away. Here, x cubed minus x cubed gives us 0. So we're left with a limit as h goes to 0 of 3x squared h plus 3x h squared plus h cubed, all divided by h. And now look, every remaining term has an h in it, which we can factor out. So if we factor out an h, we're left with 3x squared plus 3xh plus h squared. And what's h divided by h? What number is it? Thank you, yes. Right, those give us a 1. And so we're left with the limit as h goes to 0 of 3x squared plus 3xh plus h squared. We plug in 0 for the remaining h's, and we're left with 3x squared plus 0 plus 0, which is 3x squared. So for the function f of x equal to x cubed, the derivative is 3x squared. Which if you've ever seen the power rule before, you'd be like, okay, of course it's gonna be that. But it's still good to go through this process. So let's look at a couple more examples. I'm gonna try to keep things in order here. So many pages, all over the place. Okay. So let's go to the next power. This is where we're gonna see, actually let's talk, so let's talk about this pattern that I'm alluding to that I haven't actually revealed yet. So there's this really neat triangle called Pascal's triangle, which goes like this. Start with a 1 at the top, and some more 1s. And then you keep getting 1s on the sides, and the middle terms are kind of the 2 upper diagonal things above it added together. So like here, I'm going to get a 1, and then 1 plus 1 is going to give me 2. And then the next row, I'm going to get a 1, and then a 3, because 1 plus 2 is 3, and then another 3, and then a 1. And then the next row, I'm going to get 1, and then what? And so on. Next row, 1, 5, 10, 10, 5, 1, and so on and so on and so on. Keeps going. There's a lot of cool things about this triangle. One of the cool things is that every row adds up to a power of 2. 1, 2, 4, 8, 16, 32, so on and so on. Kind of a cool thing. There's lots of other really neat things. But the thing that's actually interesting, that's useful for us here, is the following. X plus h to the 0th power is 1. Okay, I know, not exciting. But hold on. X plus h to the 1st is 1x plus 1h. Okay. X plus h squared is 1x squared plus 2xh plus 1h squared. So what you might be starting to see is that each of these rows of Pascal's triangle gives you the coefficients of this binomial expansion. And it works every time. So if I want to find x plus h cubed, I know the coefficients are going to be 1, 3, 3, 1. And the pattern for how the powers work are, you start with either variable. I'm going to start with x. So whatever your power is, 3. And then you just let that variable decrease in power and the other one increase in power. So my first term is going to be 1x cubed. My next term, I'm going to let the power of x decrease and the power of h increase. So I'm going to get 3x squared h. Then my next term is going to be 3x to the 1st, h to the 2nd. And finally, my last term is 1 h to the 3rd. Each term in this expansion, the sum of the powers should be 3. So I have x cubed, I have x squared, h to the 1st, 2 plus 1 is 3, 1 plus 2 is 3. And it works continuing on. So you all could definitely write the x plus h to the 4th. Well, in fact, I would like you all to write down what x plus h to the 4th should be. I'll start you off. 1x to the 4th. This triangle is called Pascal's triangle. And I was young, great. I used to have a really cool poster of it. My mom gave me. I wish I still had it. I've tried to find it again. So I can't find it anywhere. It was super cool. I missed it. It's a great poster. These are kind of cool posters I had as a kid. Yeah.
I know that there's a way to use the same triangle for factorization of power of 2 different stuff. So like if you have 8 to the power of 2 minus b to the power of 2 and 8 to the power of 3 minus b to the power of 3, you could have, for example, 8 to the power of 5 minus b to the power of 5. And I believe there's a way to use that triangle together. But I'm not
I mean, there's definitely a way to factor the thing. I don't think you need this triangle, but I mean, yeah, certainly. Like, so I will just, sure, I'll write that down on the side here. I think that's what you're kind of thinking of.
right. So is it just Pascal without the coefficients?
I wouldn't say it's Pascal's. I don't think it's really Pascal's triangle that is involved in this particular sort of factoring.
But
Yeah.
So this is a way to do like the larger exponents without like actually foiling.
Right, exactly. So I don't want to FOIL out x plus h times x plus h times x plus h times x plus h. That's a horrible pain, and I don't need to because I can just do this. I can say it's 1x to the 4th plus 4x cubed h plus 6x squared h squared plus 4x h cubed plus 1h to the 4th. It's cool. And so on and so on. So when someone asks us to find, say, the derivative of x to the 4th, I'm gonna. Here, so by the way, instead of using this notation, so I could say find f prime of x for f of x equal to x to the 4th. But I could also write it as find the derivative of x to the 4th. Those are both notations that say the same thing, just in a different way. Either way, we're going to use limit definition. So we're going to find the limit h goes to 0 of f of x plus h minus f of x over h. And now we're good to go because we just found out that x plus h to the 4th is what it is. And now we're taking the limit as h goes to 0 of x plus h to the 4th minus x to the 4th all over h. And then we're going to, well, we're going to FOIL it out, but we're just going to use Pascal's triangle, right? We already wrote it down on the previous page. That's going to be the limit as h goes to 0 of x to the 4th plus 4x to the 3rd h plus 6x squared h squared plus 4xh cubed plus h to the 4th minus x to the 4th all over h. And then the same sort of thing that happened last time is going to happen this time. You can cancel the x to the 4th, or should I say subtract to 0. And then every term that remains in the numerator has an h in it. So we can factor out an h. So we're going to get the limit as h goes to 0 of h times 4x cubed plus 6x squared h plus 4xh squared plus h cubed all over h. H divided by h is 1. So we're left with the limit as h goes to 0 of 4x cubed plus 6x squared times h plus 4x times h squared plus h cubed. And each of these terms that have an h in it, we're going to substitute in 0 for h. So we're just going to get 4x cubed plus 0 plus 0 plus 0. Oops. So the derivative of x to the 4th is 4x cubed. And the derivative of x cubed was 3x squared. And the derivative of x squared was 2x. It's kind of looking like there might be a pattern. So what we're going to do is we're going to do one more, but we're going to make it very general. So we're going to say And this is where we're going to come back to Pascal's triangle for a second. So looking at Pascal's triangle just for a moment here, I would like to say that this top row is the 0th row. And the next row is the first row. And then the second. Then the third. Then the fourth. Then the fifth. And so if I wanted to multiply, x plus h to the fifth, I would use the fifth row. If I wanted to multiply x plus h to the fourth, I would use the fourth row. So whatever power I have, that's the row I want to use. And notably, whatever row number I'm using, the second entry of that row, and the second to last entry, but the second entry of that row is always that number, right? In the fifth row, the second entry is 5. In the fourth row, the second entry is 4, and so on and so on and so on. So if I went all the way down to say like the nth row, well, I know I'd have a 1, and then my next number would be n, and then I have a bunch of other stuff I don't know. There is a very cool formula for how to find those other numbers called the choose function. It's more important in statistics and probability than it is in this class. But if you ever want to talk about it outside of here, totally happy to. So there's the entries of my nth row of Pascal's triangle. 1, n, bigger number, bigger, up to the middle, and then smaller, back to n, back to 1. Those are my n plus 1 entries of the nth row. Just like there are 1, 2, 3, 4, 5, 6. There are 5 plus 1 entries of the 5. Okay, so we're going to use that to help us multiply out x plus h to the nth power. Let's do it. So we want to find the derivative of f of x equal to x to the nth power. Now I should point out, we are making the assumption here that n is a positive integer. This idea of writing out x plus h to the nth power using Pascal's triangle is really only valid if n is a positive integer. It doesn't really work in this way if n is some other type of number. So let's see what we've got. In fact, actually, let's just write out f of x plus h. Let's write out x plus h to the n first. So x plus h to the nth power is going to be x to the nth, or 1 times x to the nth, if you like, plus n times x to the 1 less power times h to the first. And then there's going to be some other terms. I don't know what the next number is. I'm going to call it, in fact, I'm going to call this number, so this is like my first constant. This is my next constant. I'm going to call it C2, C3, C4, all the way up to, I know there's n of them in total. 1. Right, those, I could give the constants those names of subscripts. It's a very kind of standard way of doing it. If there are n plus 1 things here, right, because there's 1, 2, 3, 4, 5, 6, 7, 8, 9, n, and then there's this other one here, n plus 1 of them. I'm going to call them that. So I know that the 0th one is 1, the first one is n, and I'm just going to call the next one c sub 2. I know there's some number, it's a constant. I don't actually care what it is, so I'm not going to figure out what it is. And it's going to be multiplied by x to the 1 less power times h to the 1 more power. And then we keep going all the way to the last couple of terms. We're going to get the second to last term is going to be n times x to the first times h to the n minus 1. Then my very last term is going to be 1 times h to the nth. Follows the same pattern as the other ones, just it's a little bit more. Questions about any of these terms here, what we've done? Yeah. I'm not, well, because I'm just kind of trying to point out that you could label all of them with this label. Right. Right. Yeah. So now let's find the derivative. It's going to be the limit as h goes to 0 of f of x plus h minus f of x all over h, which is going to be the limit as h goes to 0 of all of this. Okay, it's a lot to write again. X to the n plus n x to the n minus 1 times h. Wish my n's and my h's look a little more different. Plus c2 times x to the n minus 2 times h squared, plus all the way down to n times x times h to the n minus 1 plus h to the n minus f of x, which is x to the n, all divided by h. Just to be super clear, all of this first part, that's my f of x plus h. And that part right there, that's my f of x. Okay, so now we're going to subtract. X to the n minus x to the n is 0. So those are going to go away. And we're left with a bunch of things. A bunch of things that all have an h in them. That has an h, that has an h. The next term has an h cubed, h fourth, right? The power of h is bigger and bigger and bigger. So let's factor out an h from each of those terms. So if we do that, we're going to get the limit as h goes to 0 of h times, so I'm going to have n times x to the n minus 1 with no h because I factored out the 1h. And the next term is going to be c2 times x to the n minus 2 times h to the what? Plus a lot of other terms that all have higher and higher powers of h in them. The second to last term is going to be n times x times h to the n minus. Yeah, cool. And the last one is going to be h to the n minus. Cancel or divide the h's. H divided by h is 1. You can probably skip this step, but I'm going to write that. So now we got the limit as h goes to 0 of n times x to the n minus 1 plus a lot of other things that all have a factor of h. So all of these things all have at least one h, meaning when you plug in h going to 0, they're all going to go away. They're all going to become 0. I'm going to get n x to the minus 1 plus 0 plus 0 plus 0 plus 0 plus 0 a bunch of times. This is just going to end up being n times x to the n minus 1. And that is what we typically call the power rule for derivatives. So we have just shown, at least for positive integers, but it's actually true for any n. So this is the power rule. The power rule says that for f of x equal to x to the nth power, the derivative is equal to n times x to the 1 less power. And this is true for any real number n. Even though we only proved it was true for positive integers. Why? Pad papers I want to look at. Wait, what are they? So questions about this? Okay. So now we can just use this rule like it's always true regardless. Like we don't have. So the idea with these rules of derivatives that we're going to talk about more in depth is that we're going to move beyond having to use the limit definition. Right? That's kind of the whole point. Is we don't always want to have to be like, okay, I'm going to use limit definition to find this derivative. We're still kind of. Some classes are kind of on the brink of still having to show it. Other classes might have moved past already where they're like talk about other rules, but probably if you haven't already had your first exam will ask you to use a limit definition to show something as a derivative, and then after that we'll kind of move beyond it. But this is where we're moving towards. So let's look at a couple other examples, and we'll kind of straddle the using limit definition versus not using limit definition today. So let's look at a couple other examples about the power. So here's an example. I want to find f prime of x for f of x equal to the square root of 2x. Oh, yeah, sure, why not? Which doesn't just look like x to a power, right? I mean, there is a power involved there. You could certainly write this as f of x equal 2x plus 1 to the 1/2 power. To actually take the derivative of that using quote unquote rules, you would need, in addition to the power rule, you'd also need to be aware of the chain rule, which we haven't talked about. So since this is something I don't recognize how to do using the one rule I've talked about so far, I'm going to go back to my bread and butter. I'm going to go back to, all right, limit definition. And that's very typical. Like if you encounter a new type of function, you don't know how to differentiate, the kind of rule of thumb, at least at this stage, is to go back to the limit definition. Like, well, I don't know how to do it. So the limit definition. So we're going to find the limit h goes to 0 of f of x plus h minus f of x all over h. Let's see, that's going to be the limit h goes to 0 of, okay, let's be careful here, the square root of 2 times parentheses plus 1 minus the square root of 2x plus 1 all over h. And what's going in our parentheses there? Yeah, exactly. That looks terrible, but it does look like a 0 over 0 type of limit. And we've had some practice with 0 over 0 types of limits. Especially when we see square roots, a common thing to do is to multiply by the conjugate. That's what we're going to do here. We're going to multiply the top and bottom by the conjugate of the numerator. So it's going to be equal to the limit as h approaches 0 of the square root of, I might do a very small simplification here and say that's going to be 2x plus 2h plus 1. It's not particularly necessary, but it feels silly not to do. So I've got the same expression and then multiplying by the conjugate of this. So it's going to be times the square root of 2x plus 2h plus 1 plus the square root of 2x plus 1, all divided by the same thing. Okay, so now we simplify. Multiply at the top. We're going to, so the whole reason we multiply by the conjugate is so that the middle terms cancel, right? Multiplying this by its conjugate, you just get the first thing squared minus the second thing squared. So we're going to get limit h goes to 0 of, so the square root squared gets rid of the square root. We're going to get 2x plus 2h plus 1 minus the second thing squared, which is 2x plus 1. You could write out the middle terms. The middle terms would be this square root times that square root minus this square root times that square root, which would totally cancel each other out. Subtract the 0. Divided by, okay, I'll remind you, whenever you multiply by a conjugate over a conjugate, you actually multiply out the conjugates and you actually don't multiply out the not conjugates. So right, I want that h to cancel. I want this h to cancel. There's no good reason to multiply it through to everything if I know I want it to cancel. I'm going to leave it out in front. I've got all this hot mess over here. 2x plus 2h plus 1 plus the square root of 2x plus 1. Okay, now we can simplify the numerator. I can see that 2x minus 2x is 0 and 1 minus 1 is 0. So I'm just going to be left with the limit as h goes to 0 of 2h on top over h times all this stuff on the bottom. We're almost there. Now h divided by h is 1. So we're left with the limit h goes to 0 of just 2 over square root of 2x plus 2h plus 1 plus the square root of 2x plus 1. And finally, we have gotten to a place where we've gotten rid of that first initial h in the bottom, and now we can substitute in 0 for the rest of the h's. So if we plug in 0 for h, we get 2 over square root of 2x plus 0 plus 1 plus the square root of 2x plus 1. And when we add those two square roots together, be careful. I've seen a lot of people in this situation want to multiply them and say we have 2x plus 1 on the bottom. We don't have 2x plus 1 on the bottom. We have 2 times the square root of 2x plus 1 on the bottom. So this is going to be 2 over 2 square root 2x plus 1. And then you can cancel the 2's and say you have 1 over the square root of 2x plus 1. This does not seem like an unreasonable limit definition of a derivative question on the exam, but it's certainly on the upper end of being harder. Typically, if I was asking a limit definition question on a test, I would probably ask one that was more like x to the third or x to the squared plus 4, like something that was more polynomial. It gets a little bit more challenging when it's a square root or a rational function. Questions or thoughts about what we've done here? Yeah. Which so from where to where? So I added them together. So if I have something plus the same, right, because they're the same, because the h went away and was 0. So if I have a thing plus the same thing, I have 2 of those things. And then the 2's canceled. So that's why we only have 1 of them left at the very end. Yeah, we should do one other one. Let's see. Yeah. So let's look at one more limit definition example that comes up maybe some often. Ooh, yeah, we'll do this one kind of both ways. So let's say we want to, for f of x equal to 1 over x, we want to find the derivative. Now, first of all, note that the power rule could be used here. Now, I should also point out, on an exam, if someone says use the limit definition of the derivative and you just use the power rule or whatever rule might apply, you'll probably get very little to no credit. So make sure that even if you know how to do it a shortcut way, if they say use the definition or use the limit definition, that you do it this long limit with h goes to 0 kind of way, even if it's not. So I'm going to pretend like they said use the limit definition here. So I'm going to take the limit as h goes to 0 of f of x plus h minus f of x all over h. But off to the side, I'm going to tell myself, well, even though they didn't ask me to do it using the shortcut, I know what the answer should be using the shortcut. Right? If I write my function as x to the -1 power, I can find the derivative using the power rule and say, oh, that's going to be -1 times x to the -1 minus 1, which I could simplify. That's -1 times x to the -2nd, or if you prefer, -1 over x squared. So not that that gets me any credit really, but it lets me know what the answer should actually look like. It's also good to see, just because that'll actually show us that even for powers of x that are not positive integers, we're going to see that after doing the limit definition, the power rule still does work. It gives us the right answer. So let's see what we get here. So the limit as h goes to 0, f of x plus h is going to be 1 over x plus h. Of x is 1 over x all over h. I do not love fractions and fractions. So here's what I might do to make it so I don't have to write fractions for fractions. I might totally just rewrite this as the limit as h goes to 0 of the stuff on top, 1 over x plus h minus 1 over x. Instead of dividing by h, we can multiply by 1 over h. It's no different, it's still the same problem. I'm just writing it in a way that I feel like is easier to write. All right, so if I want to subtract these fractions, I need something. I need the common denominator. I need to multiply x plus 1 over x plus h by x over x, 1 over x by x plus h over x plus h. So now we have the limit as h goes to 0 of, so inside these parentheses here, I have x over x times x plus h minus x plus h over x times x plus h. I can combine those two fractions together. That's the whole point of getting a common denominator. I can subtract those fractions and get the following. Limit as h goes to 0 of something over x times x plus h times 1 over h. And here's where you have to be a little bit extra careful. When you're subtracting a fraction, if the fraction has multiple pieces added together, you're subtracting each one of those pieces. Or in other words, this minus sign distributes. It's really going to be x minus h. This is actually where it's like let's just all say this at the end, sure. We'll come back to this. I'll make a comment. I have enough room? Yeah, I have enough room. So x minus x is 0. So I'm left with the limit h goes to 0 of minus h over x times x plus h. You could still say times 1 over h, or you could just put the h in the denominator we already have. So it's perfectly fine to write 1 over h. It's also fine to just say the h can live there if you want. Either way, it's fine. And then h divided by h, it's just 1. So I'm left with the limit as h goes to 0 of -1 over x times x plus h, letting the rest of the h's go to 0. You get -1 over x times x plus 0, which is just -1 over x squared. As expected. Here's what I want to say about this. If we had made an error, right? If this had actually accidentally been a plus h here, we would have gotten a +1 on top here. We would have gotten a +1 over x squared. That's where having done this really kind of pays off. We're like, oh, we know the answer should actually be -1 over x squared. I'm getting +1 over x squared. Where am I missing a minus sign? And then we can kind of go back and work and look like, oh yeah, I misdistributed the minus sign there. So that's why it's kind of helpful to be like, even though this doesn't really get me any credit, it is nice to know what answer we're looking for. I will also point out the flip side of that is that you might have done all the work for the limit definition mostly correct and done a lot of work that will get you some partial credit, and then you're seeing the answer is not right. If you see that, don't just erase all your work, right? Leave it there, look for, or maybe just leave it there and come back to it later, right? If you're taking a test, your time is limited. So definitely, if you get to something, you're like, well, shoot, I know it's mostly right. I did the limit definition. I'm off by a minus sign. Maybe go back and look, but if you're not finding it, don't just like cross out your work or erase your work. Leave your work there so that you get some partial credit. And if you have time at the end, come back and be like, okay, let me see what I can find where I'm making this. But don't stress too much about trying to make it look perfect. Partial credit is a thing most teachers should offer, I hope. I mean, it depends on the class. I don't know, not everyone's the same, but usually there is the opportunity to get partial credit. Definitely, if you've written work, don't erase it or scratch it out unless you absolutely know it's totally incorrect. It's worth leaving there so that you can at least get a chance at some partial credit. Okay. So yeah. So one more example here. So back to the power rule. Again, the power rule says that your function x to some power, your derivative is that power times x to the n. People often say the words like the power comes down and then my new power is 1 less. And there's a lot of things we do that kind of that we don't really think about what we're doing. So for example, if I said my function was 9x to the 4th plus 7x squared minus 5x to the -6th, I'm going to use the power rule. So for this first one, I'm going to get down the 4, 36 times x to the 3rd. Now, I did something there that we didn't even talk about, which is that constant 9 just sticks around. And so what I'm really doing is I'm bringing the 4 down. I'm getting 9 times 4, which is 36 times x to the 1 less power. And similarly here, what do you think we're going to get here? Yeah, 14x to the 1st. And then here we're going to get 30x to the -7. So what we're doing here is we're using a couple rules. Actually, we're using like 3 rules that we, again, so much like there are those limit rules that we use all the time and we never actually explicitly write out. There are rules for derivatives that we use all the time that we never really explicitly write out. One of those rules is that if you're taking, say, if your function is a constant multiple of another function, and you take its derivative, the constant multiple just hangs out. So you have a constant times the function, you take its derivative, you have the constant times the derivative. Which is what's really happening here, because what we're really getting here is that, oops, oh, I made not a huge error, but I made an notational error. I shouldn't have written that this was equal to this. I should have said f prime of x is equal to that. Not equal to the function, derivative. But what we're really getting here is 9 times 4x cubed. We're taking the derivative of x to the fourth and multiplying it by 9. What we're really getting here is 7 times the derivative of x squared. What we're really getting here is -5 times the derivative of x to the -6. But we never really think about showing or doing that. It just kind of happens almost automatically. The other thing I used here, which also is something that we use all the time without ever saying it, is that I took the derivative of a bunch of functions, added together or subtracted together, and I just added or subtracted together the results. And that's kind of another thing. If you want to say take the derivative of a function plus another function, it is just the derivative of the first function plus the derivative of the second function. Or you can also subtract them. So these are two rules we use all the time that we never really think about using. So for example, if I wanted to find the derivative of 6x to the fourth plus 7x to the third plus 9, I'm just going to use those rules. I know that I can take the derivative of each one of these. The 4 comes down and multiplies the 6, 24x cubed. The 3 comes down and multiplies the 7, I get 21x squared. And oh, derivative of 9. It is 0. Why? Well, I would say yes, but so it is 9 to the power of 1. What's the power of x? 0. So you could, one way to think about this is you could think of 9 as 9 times x to the 0, and then the derivative would get you 9 times 0 times x to the whatever, which is just 0. But really, the kind of more typical way of thinking about why its derivative is 0 is because, well, I know how to graph y equals 9. Pretty easy to graph. It looks like this. And what's the slope of that line? 0. It's got a 0 slope. And the derivative, one interpretation of the derivative is it's the slope of the, well, I should really say it's the slope of the tangent line, but any tangent line would just be the line itself for a straight line. So here, y equals 9, the slope is always 0. So the derivative is always 0. So that's why constants have a derivative of 0, because there's also, we could also use the limit definition derivative of the derivative. So let's actually do that real quick. Yeah. If my function was 9, which is not super exciting, let's find the derivative. Okay, so it's going to be the limit. H goes to 0, f of x plus h minus f of x. This actually points out something fairly important. Okay, that's the limit. H goes to 0 of, help me out. What's f of x plus h? What's f of x? Also 9 divided by h. Just to make sure everyone's super clear with that, right? There's x. F of x is, oh, it's 9. There's x plus h. Oh, f of x is also 9. Now, this is not, although it kind of looks like it, it's actually not really a 0 over 0 type of limit. So Okay. So let me ask everybody. Take the limit as h approaches 0. H isn't 0. H is getting really close to 0. And if h is a really small number, it's not 0. What's 0 divided by not 0? 0 divided by not 0 is 0. So we do the division first. Okay, so that's the limit. H goes to 0 of 0. And oh, the limit of a constant is just the constant. It's something that comes up often, where something kind of looks like it might be 0 over 0, but really it's 0 over something that's approaching 0. And so you can do the division first, just get 0, and then take the limit of it. It's kind of weird. It feels a little like I'm lying, but I'm not. It's for real. This actually comes up a lot in 21C. So later on in your calculus career, you'll see this kind of thing happen again, where this type of trickery, for lack of a better word, comes up. So yeah, so that's going to be 0. And then we wouldn't write it. I would just write 24x cubed plus 21x squared. Question? Well, so the difference is no. So for example, if I had just to kind of contrast that, the limit as h approaches 0 of say 2h over h. Sorry, you can't see that. That is an actual 0 over 0 type of limit. So when you see what a 0 over 0 type of limit is, it really should be each part is approaching 0. It's not that it's actually equal to 0 all the time, it's approaching 0. So here, if I plugged in 0 for h here and 0 for h here, I get 0 over 0. And so then I can say, well, those are going to cancel. I'm at the limit as h approaches 0 of 2, which is just 2. Is that what you were asking?
I think because h is approaching 0, but once the top is twice the bottom.
Right, exactly. Yeah. I guess it's 11:49, and I should not try to cram in another example.